For this section, we are looking at how to calculate concentration of a solute in a solution in molarity. And molarity is units of moles per liter. And use the solution concentrations in calculations. And then describe how to prepare a solution of a given concentration from the solute and the solvent, or by dilution of a more concentrated solution. Most chemical studies require quantitative measurements. Chemistry, a huge part of chemistry is quantitative, giving numbers, right? Quantities. Experiments involving aqueous solutions are measured in volumes of solution rather than masses of solids, liquids, and gases. So we're looking at volumes of solutions. Solution concentration, which is expressed as molarity, relates the volume of solution in liters to the amount of substance in moles. Notice, if we were to weigh the amount of a substance on a scale, we would measure the amount in grams, but we always need to convert it into moles. So, our qualitative versus quantitative. Qualitative, we would say that something was concentrated or that it was diluted. Think about if you were to make a Kool-Aid or a lemonade solution. If you put a lot of scoops of that powder in with, let's say, in 1 liter, versus, let's say you have 1 liter of water and you put 1 scoop in. If I was to qualitatively describe that, I would say, ooh, the one with a lot of scoops was very concentrated, and the other one was very diluted. Well, but using our quantitative measurements, we would be able to specify the amount of solute and solvent in a solution. We can look at mass percentage, and we can look at molarity. So a solution is comprised of 2 pieces. In a solution, we have the solute and we have the solvent. The solute is what is being dissolved. The solvent, what is doing the dissolving. So here in this picture, they measured out exactly 1 liter of water, which was slowly added to the flask. And in the flask, there was 25.0 grams of this copper sulfate pentahydrate. Okay, so we had grams of a substance, which we know we can get to moles. And then we have 1 liter of our solvent, what's doing the dissolving. So we can find out this concentration. And again, molarity is moles of solute per liter of solution. Per liter of solution. So we use that, our unit is moles per liter, or it's symbolized with a capital M. So if you see capital M, if I said, also it's signified by brackets. Brackets means concentration. So if I said my concentration of NaCl is 1 m, that means there's 1 mole of sodium chloride in 1 liter of water or solution. So we have a solute. It's usually in a solid form, and it's soluble salt or a soluble covalent compound. Again, we need it to be dissolved in solution. A solvent is considered to be the major component. Usually it's water. So let's look at preparing a solution where we know the concentration. In lab, you've seen lots of chemicals that are labeled 0.1, capital M, which is molar, of HCl, or 2.0 molar HCl, or different concentrations of all sorts of different chemicals. Well, here's what we do. We start with a certain size of a volumetric flask. Volumetric flask is a much more precise way of measuring than, let's say, a beaker. So we use a volumetric flask. In this case, we have a 250 milliliter volumetric flask. And I weigh out a certain amount of my solute. In this case, we have 0.435 grams of potassium permanganate. Then, so I know my grams, which I can get to moles, And I'm going to fill it up all the way to the 250 milliliter mark. We put in just a little bit, I don't know, maybe a third of the way up. We fill it with water and you dissolve it. So you dissolve it in a small amount of water, and then you go all the way up to the neck where there's a line, just like with pipettes. That tells us that our volume is exactly at 250, notice that there's a point, milliliters. And just like that, we have a solution. We can then get our grams to moles, and then we would divide it by liters, and in this case it would be 0.250 liters. And so however many moles that is, we would just do moles divided by liters, and that would give us our concentration of that solution. So this is just telling us again, you weigh out your solid solute, transfer it to the flask, dissolve it in your solvent, which you want to do it less than all the way up to the where it's all the way full. So do it in a half amount, third of an amount, and then you fill it all the way up to the calibration mark. And then you invert your flask, you put a stopper on the top of your flask, invert it, shake it up as many times to make sure that it's all mixed up. So let's look to see what this concentration would be. If I had 0.395 grams of KMnO4 and enough water to give us 250.0 milliliters of solution. So notice I went from grams to moles using the molar mass. I should have gone to another significant figure here. And then once I have moles, I'm going to divide it by liters. So 250 milliliters is 0.250 liters. And again, it can be denoted as in brackets. Sometimes it's also written like this, the C, the concentration of KMnO4. And here's our answer, 0.010 molar, and there should be one more digit. Let's add that to it. There we go, 3 sig figs. After doing the math, we just need an extra 0. So 0.00100 molar. That means moles per liter. How about you try this one? We're going to dissolve 5 grams of nickel chloride hexahydrate in enough water to make 250 milliliters of solution. Calculate the molarity. Why don't you pause the video and see if you can set this up. First we want to calculate moles. If I have grams, so 1 nickel, 2 chlorines, and 6 waters has a mass of about 237.7. So that would be moles of the nickel chloride hexahydrate. And to find the molarity, if we've got moles, we're going to divide by liters. This just shows you going from milliliters to liters. You could also just take your moles and divide it by, if you did your milliliters to liters, separately, 0.250 liters. And you should get with 3 significant figures, 0.0841 molar. Now let's look at what ions we have in a solution. If I have copper chloride, copper 2 chloride, and it's an aqueous solution, so it dissolved, we have 1 copper and 2 chlorines, correct? So 1 copper, which is a Cu2+, and 2 Cl- ions. So for every 1 copper 2 ion in the solution, there are 2 chloride ions. So if I said the concentration of my copper 2 chloride solution is 0.3 molar, so let's look at our stoichiometric ratios here. Got 1 to 1 to 2, right? If I look at my balanced equation, on the left side I have 1 copper chloride, and in that copper chloride there's 1 copper, so 1 copper. There's 2 chlorines, so that's why I have a 2 over here. So if I said my copper chloride concentration was 0.30 m, I would say for every, and this is for CuCl2. Well, 1 CuCl2 for 1 Cu2+, obviously 0.3 times 1 divided by 1 is 0.30 molar for the concentration of copper plus 2. Let's look at the concentration for the chloride ions. Obviously we can see just by looking at it that there's 2 chlorides for every 1, so it's going to be a greater concentration of those. But let's look at it mathematically. 0.30 molar of CuCl2. There's 2 Cl minuses. So 0.3 times 2 is 0.6 molar for the chloride ion concentration. So let's look at this. What's the concentration of each ion present? If I have 0.1 molar of KCl, what's the concentration of K and what's the concentration of Cl? Well, for every 1 KCl, there's 1 K and there's 1 Cl. So these are all 1 to 1 to 1 ratios. So whatever my concentration of KCl is, it's going to be the concentration of K and it's going to be the concentration of Cl because it's all 1 to 1. But let's look at this guy, magnesium nitrate, MgNO3 2. When this breaks down, I'm going to have magnesium plus 2 ions and NO3 minus ions. And again, I balance it. I have 1 magnesium, 1 magnesium. On the left, I have 2 NO3s, so I would need 2 NO3s on the right. So my magnesium nitrate and magnesium are 1 to 1, so they would be the same concentration. But if I said I had 0.25 molar, we know that for every 1 of magnesium nitrates, there's 2 NO3 ions. So 0.5 times 2 will give me 0.5 molar for my NO3 minus ions. Let's look at this. Lithium carbonate is a salt used to treat manic depression. What mass of lithium carbonate is required to prepare 500 milliliters of a 0.250 molar lithium carbonate solution? Okay, so I'm going to show you a little trick here. Remember the trick where I showed you that density is equal to mass divided by volume, and you cover up what you want to find, right? If I wanted to find density, it's mass divided by volume. If I wanted to find mass, it was density times volume. If I wanted to find volume, it was m over d. Well, let me show you how we could set that same thing up. We know that concentration is moles divided by liters. So let's look at what we want to find. What mass? Now, of these 3 units, mass is not one of them, but can I get to mass easily from one of those units? Sure. If I can find moles, I can get to grams pretty easily. So let's look to see how, if I need to find moles, moles is molarity times the volume in liters. Okay, let's see what we've got. What mass of lithium carbonate is required to prepare 500 milliliters, which is 0.5 liters, and do I know the concentration? Yep, 0.250 molar. So 0.250 capital M times 0.5. That should give me 0.125 moles of the lithium carbonate. Now, for 1 mole of lithium carbonate, we were told it has a weight of 73.9 grams of lithium carbonate. Times 73.9 should give me, with how many significant figures? 3. 9.24 grams. How about you try to calculate the volume needed to make this solution and the volume needed to make that solution. Why don't you pause the video and try to work those out? Okay, the first one, I was told to calculate the volume. We were given the concentration and we were given moles. So using my little circle guy up here, liters or volume is equal to moles divided by molarity. So I plugged in my 0.01 moles divided by 0.250 moles per liter. That gave me 0.0400 liters. Make sure you have 3 sig figs. And down here, volume, again, I'm still doing moles divided by concentration, but I was given concentration. I plugged that in, and we were told 8 grams of the lithium carbonate. So I did grams to moles first, plugged in for my top number, divided by 0.250, and I got 0.433 liters. Now, how do we prepare a solution by dilution? Okay, so let's say I'm starting with a 0.1 molar potassium chromate solution, and I want to dilute it. Okay, so we're going to use a pipette to withdraw a certain amount of a certain concentration, and then we're going to put it into another container. In this case, we put it into a 500 milliliter flask, and then we fill it up to the top. So we know the final volume. So if I know my first volume that I'm taking and the first concentration that I started with, and I know that I'm putting it into another container and I know that second volume, I can find that second concentration. All right. So we know that when more solvent is added to a solution, the concentration of the solute decreases. So obviously, this should make sense. When my denominator gets bigger, so when that liters of solution increases, when the denominator gets bigger, it's kind of like saying 1/2 versus 1/4. My denominator got bigger. If I add more solution and my moles of solute stays the same, notice what happens. 1/2 is much greater than 1/4. Notice that my concentration is getting smaller. 1 divided by 2 is 0.5. 1 divided by 4 is 0.25. My concentration just got a lot smaller by that denominator increasing. So let's say a student adds a 50 milliliter aliquot to a 0.515 molar HCl solution to a 500 milliliter volumetric flask. She then filled the flask to the calibration mark with water. What is the new molarity of the HCl? Well, first thing we did was went from milliliters to liters right here. So that would give me 0.0500 liters. And then we knew the concentration, which is 0.515, and we know that molarity means moles per liter. Notice how liters and liters will cancel out. Okay. Now I am left with, my answer will be in moles, and I'm going to divide by my new volume, which is 500 milliliters or 0.5 liters. And this was them just going from milliliters to liters. Okay. Another equation, a simpler equation. I like this one. Like I was telling you, if I know my initial concentration and how much volume I take of it, and what the final volume is I fill it up to, I can find that final concentration. I like to simplify this equation by saying M1V1 equals M2V2. Sometimes this M, you might see it in your worksheet or in your book as C1V1, and that's for concentration versus molarity. They're the same thing. C2V2. Okay, let's look. What volume of 12 molar of HCl is required to prepare 100 milliliters of 1 molar HCl. So let's look at what we know. We know that we have a very concentrated, so this is my M1 concentration. It wants what volume of it is required to prepare. This is the volume I'm preparing, this is the concentration I'm preparing. So I know 12 molar, that's my M1, V1 is my question mark, my 1.0 molar is my M2, and my V2 is 100 milliliters. Here's what's nice about this calculation. If I have molarity and molarity, we're good. For volume, volume doesn't have to be in liters. If this unit is in milliliters, this unit will be in milliliters. Same with if this was liters, this would be, the second one would be in liters. You don't need to convert it into liters. I mean, you can if you want to, but you don't have to. I mean, unless it said what volume in liters. But in this case, it doesn't tell us that. So to solve, we're just going to do some simple algebra, divide both sides by 12. So our molarity cancels out, and we're left with V1 is equal to 8.3 milliliters. Let's try the second one. How about you try setting it up? What's the concentration of a solution prepared by diluting 25 milliliters of 14.8 molar of nitric acid to a total volume of 1.5 liters? Be careful of your units. Okay, now it wouldn't matter if you put milliliters into liters or liters into milliliters. You will get the same answer. Okay, so I found that this was my first volume and this was my first concentration, and this was my second volume. I need to find my second concentration. And you should have gotten a concentration of, with 3 significant figures, 0.247 moles per liter. Here are some join-in questions that you should move through slowly. Pause the video, try them at your own